So, not a lot of you here today, so I don't know how people think they're going to learn it, but I guess here we are. So, so we left off kind of with this idea of linear regression. Before I kind of go here, just to kind of set this up, before we jump into material too much, I do want to point out, because I think just to show you guys where it's at. So under files, I put this final exam material folder. So you've got a couple practice exams with the answer keys. You've kind of got the formula sheet and then the tables that you'll have for the exam. Other than that, shouldn't be anything kind of housekeeping wise to take care of. So unless there's any questions from you, kind of jump into the material. Okay. So we were, thinking about, let's say when I had a sample mean. This was kind of our test statistic equation, right? Let me see if this, zoom in a little bit. There you go. So what we're going to do with our coefficients, so we're looking at that intercept and we're looking at that slope coefficient, right? We said it's kind of like they're just estimates, right? So when I'm thinking about running this regression, a lot of the times we'll write this, instead of using A and B, kind of using this Greek letter beta. Right? So we're going to come up with, from our regression, essentially estimates for what these two values are. Right? That was the whole goal. What two values would minimize the sum of those squared error terms? So the way we're going to calculate our test statistic, you kind of think about it is no matter what beta we have here, right? Beta 0, beta 1, we'll kind of talk about today. We actually can include several variables here on the right-hand side. We see that estimate for what that coefficient is. We're going to have some assumed true. So it's a little bit here, I think what I use in the slides is actually gamma zeros, just so we don't confuse kind of the intercept with what this assumed slope coefficient is. And then just like before, we'll divide by the standard deviation of the statistic that we're interested in. Now, what we're going to end up calling this is our standard error. Okay? The null and alternative hypothesis that we're going to use is we're always going to start out, right? What we're trying to find is there a relationship between this X and Y variable? So this gamma, right, or we're going to call it kind of like the true population coefficient. We're always going to be testing to see, is this not equal to 0? Or said differently, we're going to assume that it's equal to 0. So we start out always assuming that there's no relationship between this X and Y variable. This will always be our null and alternative hypothesis. So we don't have to worry about identifying it. This is always what it's going to be. Right? We're going to assume that that relationship is 0 because we're trying to find whether or not it's not equal to 0. So this test statistic equation kind of simplifies. If this is always 0, our test statistic is always simply going to be that coefficient, that sample coefficient we find, divided by its standard error. And this standard error is going to be one of the things, or one of the outputs that Excel gives us. Right? So we're going to be able to see these values in Excel and kind of think about this standard error. It's like the standard deviation of the statistic we're interested in. That's exactly what we were doing before. So I'll show you the equation for how you calculate the standard error, but we're never going to have to. Excel is going to do that for us. And then once we have this test statistic, the degrees of freedom, we're not going to kind of talk about it. It's a little bit more complicated than kind of just working with like those one population examples where it's n-1. But Excel knows how to calculate the degrees of freedom. And then we'll always look up, use that test statistic, and find the p-value associated with kind of the sample coefficient that we found. So it's the same general idea of what we're doing before. It's just we don't have to do all the steps. We don't have to calculate this standard error given to us. We don't even have to look up this t-value from the student t table. We're always going to be given that p-value. Now our rejection decision is exactly the same as it was before, which is just, is that p-value less than alpha? Right? So we're just going to go through and see, is my p-value associated with this coefficient, sample coefficient? Is it less than my benchmark values of 0.1, 0.05, or 0.01? Right? So everything's going to be exactly the same as it was before when it comes to that rejection decision. It's just it's easier to get that p-value because Excel is going to give it to us. Okay? So we're always going to have what type of tailed test? Always a two-tailed test. We're always only going to have like this sample kind of, there's a sample variance if you want to think about it kind of built in here. So we're always going to be looking at that student t-distribution and have a two-tailed test when it comes to doing this linear regression hypothesis testing. But like I said, we're really skipping a lot of the steps. We're just going to kind of be right there and we'll always have that p-value. Okay. So we'll kind of see what this looks like as we work through a few examples. So here is, right? We could do a left, we could do a right, or we could do a two-tailed test. But what we're always going to do is use a two-tailed test. We're not going to assume anything about the relationship between X and Y, right? If we wanted to do a left or right, we're kind of assuming, well, we think that it's, you know, a positive, or we think that it's a negative. No, we're just going to assume we don't know anything about what this relationship is. Just, is it different from 0? Okay. So if we looked at kind of some linear regression output, and this one, I think I had birth weight as my Y variable, or the thing that's going to depend on my independent variable, which was just, did the mother smoke during the pregnancy or not? So here, my smoking variable is just a 1, 0. So this brings up kind of our interpretation sometimes can be a little bit different. So we said last class, the interpretation of this coefficient on the slope B will always be the effect of a 1 unit increase on X on the predicted value of Y, right? Because if X goes up by 1 unit, then Y goes up by whatever B is, right? That's kind of the definition of a slope. And so when I have a 1, 0 variable, a 1 unit increase is going from the group that's a 0 to the group that's a 1. So here, someone who doesn't smoke during pregnancy, or sorry, relative to someone who doesn't smoke during pregnancy, if they did smoke during pregnancy, we would expect this birth weight to go up or down by whatever that slope coefficient is. So the 1 unit increase simply means if I was to go from the group that was a 0 to the group that was a 1, that's my 1 unit increase. So here, a mother who doesn't smoke to then going to a mother that does, the expected change in the birth weight would be 213 grams lower, right? There's a negative coefficient. So how would I find, so that's just kind of our interpretation. How would I find my test statistic? Well, I've got my coefficient. This is kind of like my beta hat that I was showing you before. So let me blow this up so you have this. All right. Here's my slope coefficient, just divided by my standard error. So notice here, just take negative 213 divided by 48.9, right? I mean, if I round this pretty bad, right? 200 over 50 is about 4. It's negative, so negative 4.36. If we actually get that entered into our calculator, I just kind of eyeballing it there. It's about 200 and it's about 50. So our test statistic should be around 4 there, right? 200 over 50, or sorry, negative 200 over 50. And I think what I actually did in these slides, and I do this a lot in this regression output, so just so you're aware if you're looking at it, I just kind of put like a blank box over this because obviously this output, Excel is always going to give us, or these other statistical programs will always give us all this output. And so there's no reason it shouldn't be there. I'm just kind of doing that so that we can't see the values, right? So you can always kind of move that. So you can kind of see here, I could also do the same thing for the intercept. I could take my coefficient of 3,427, divide it by that standard error of 14.29, I would get that test statistic of 239. So here, you know, that test statistic's very, very large. It still has the same interpretation. It's how many standard deviations away from that assumed true value, which will always be 0 here, was our sample coefficient. So both of these essentially have p-values of approximately 0, right? They're out to the third decimal, they look like 0. So we would say that we could reject the null hypothesis for both of these, both the intercept and that slope coefficient. Now, we generally aren't concerned with doing this for the intercept just because it doesn't have a lot of relevancy to us. But for the variable that we're interested in, here being able to reject the null, remember, the null, we want to think about gamma or this beta, we're assuming it's equal to 0. So if I can reject that, what I'm really saying is I'm rejecting that there's no relationship between birth weight and smoking during pregnancy. Or said differently, I found strong evidence there is a relationship, right? Because I can reject that there's no relationship. I found evidence that supports the alternative hypothesis, which is there is a relationship between these two variables. Okay? And I could do that at any level of confidence here, right? Because if a p-value is 0, it's going to be less than any alpha that we look at. Okay. Any questions over that? Keep moving. So here, if I ask you to calculate a test statistic on the exam from some linear regression output, it should be very easy. It's just one of the easiest things, hopefully, that we've done this class. All you do is take that coefficient and divide it by the standard error. It's a very simple equation. Right? So let's think a little bit more about this. We already went through this last class, thinking about the errors, blah, blah, blah. I said, if we have time today, maybe I'll show you how to break it down step by step. But the real thing I want to kind of talk about and discuss today is we have thought about simple linear regression, one y variable and just its relationship with one x variable. But I kind of alluded to at the end of class, well, if I'm trying to predict income, I need a lot more than just one variable. I'm going to need several variables. So what I can do is I can include as many variables as I want within, well, there's some exceptions to that, but that's outside the scope of this class. For the sake of this class, I can include as many, variables as I want on that right-hand side. Okay? And now the interpretation is going to become a little bit more powerful, right? So Excel can run this regression output for me. So we want to think about this as, let me see here. Here it is. I'm still minimizing the sum of my squared errors. It's just now, instead of just choosing the intercept and the slope, I have to choose the intercept, this slope, this slope, this slope. Right? I've got way more variables that I'm selecting off of. And so I have to take a derivative of this equation in respect to every single coefficient. So now I'm going to have n equations and unknowns. This is going to become a lot more difficult algebra. In fact, to really solve this, we're going to end up kind of using some linear algebra, but we don't have to worry about that. Excel's going to do all that for us. Okay? So it's a little bit too complicated for this class. There's this kind of good resource from this guy at UC Davis. He kind of walks through how you would solve through it. And if you math heads, I guess, or you can kind of look at that, although I doubt anyone's going to really want to go through that proof. But everything is the exact same. Once I get those coefficients from Excel, the interpretation is still the effect of a 1 unit change in X on the predicted value of Y. It's just now we add on this term at the end, which is holding everything else in that regression constant. So you can imagine this becomes pretty powerful, right? Every other variable that I can put on that right-hand side, now the interpretation of that X variable I'm interested in, that coefficient, is holding all these other factors constant. So I think here, I had this policing example, and we'll kind of walk through one in Excel today. But if I include just the relationship between, let's say, crime rates, and actually I think here I'm using beta, so I'll start using beta. So I've got my intercept, and maybe I'm thinking about what's the relationship between police force expenditures and crime rates across different counties. So I run this regression, I get the output from Excel, and what I end up finding is that my slope coefficient is positive, that the relationship between police force expenditures, measured by the dollars spent on my police force, and the crime rate in a county, it's actually positive, which would mean for every additional dollar I spend on my police force, crime goes up. Right? So that sounds kind of weird, right? I mean, it seems like a weird relationship, but we have to remember, this isn't causal. It's just correlations. Right? And so why might counties that have that are spending more on their police force have higher crime rates? Well, it's likely that areas that need to spend more on their police force, probably it's because they have higher crime rates, right? And so it's all these other factors that are probably driving up crime will also be related to how much I'm spending on my police force. So I want to try to control for those other factors. So what I can do is include additional control variables there. Now, when I run this regression and I get my output, the interpretation of this slope coefficient, it's still the effect of one more dollar spent on my police force on the predicted crime rate. But now it's holding constant the unemployment rate of the area, right? And so that becomes a little bit more powerful because now the thought experiment, like the hypothetical that I'm able to make the statement of, is two areas with the exact same unemployment rate. but one of those counties spends $1 more on their police force, how much would you expect crime rates to change, go up or down, depending on the sign of the coefficient? And not only can I control for the unemployment rate, I can control for the average income in the area. I can control for, other kind of socio-demographic kind of variables that I think might influence crime, maybe age demographics, things like that. And so I can really make some powerful statements, right? And we'll see this, I think, play out in the Excel example I have. I'll show you what happens if we include, like 5 or 6 other variables over here. Okay. So I'm not going to worry about the math here. I don't know why I have, of course, here, but the other one statistic that we're going to discuss a little bit is R-squared, right? So R-squared is going to be a measure of how much of the variation in our Y variable we are able to explain with the independent or those X variables that we've included on the right-hand side. So if we think about this example here, if I run this regression, Excel gives me all this output. One of the things it gives me is this R-squared statistic. So R-squared here would reflect the amount of variation in crime that I can explain with just police force expenditures and the unemployment rate of a county. So you can imagine, as I add in more variables, what probably happens to R-squared? If I think about the percent of the crime rates I can explain with 2 variables, what do you think happens when I have 12 variables on the right-hand side? R-squared is going to go up, right? The more data, the more variables I have, the better I can explain why a variable's value is changing. Right? So by including additional variables here on the right-hand side, we're going to be able to drive that R-squared up or explain more of the variation in crime rates. Or said differently, we're going to be able to come up with better predictions for what that crime rate is. Right? So higher R-squared means we can come up with better predictions for our Y variable. So here's kind of the mathematical of what we're measuring. Now, I'm not going to make you kind of calculate this ever, and you're going to be given it in Excel. It's one of the statistics it gives you. But you can kind of think about, it's really this ratio of, if I take all my predictions, the difference between my predictions and the average Y. So how do I come up with my predictions? Well, my predictions are based off of only the variables I've included on the right-hand side there. I then look at, well, what's the actual Y value's difference from the average Y? Well, that's going to explain all of the variation, right? So my denominator here, this total sum of the squares, this is like capturing the total variation that exists in the actual Y values. And then the numerator is, well, how much variation is there just from my predictions? And whatever my predictions are missing, that's kind of like the gap, right? So maybe the total sum of squares here, let's say I had a variation of, 100. And then when I'm looking at the variation that exists in my predictions from the average Y, maybe it's only, 85. Well, that would be, I'm explaining 85% of the total variation. Now, it usually doesn't work out to be nice numbers like 85 and 100, but that's the general idea, right? I've got the total variation in my denominator, the amount of variation I see from my predictions. So that's how much, or the proportion of the variation I can explain with whatever variables I've included on the right-hand side. So we'll look at R-squared. We'll generally think about, as we include more variables on the right-hand side there, we can drive R-squared up, which is good. It means we're able to make better predictions. There's like less error term that we can't explain. So when we include all these variables on the right-hand side, I kind of mentioned with a crime example, maybe once I include the unemployment rate of an area, so I say, okay, I found a negative coefficient before, but I'm going to control for kind of like the economic conditions of the area, which we know are probably going to drive up crime rates. So now when I include this additional variable, what I actually end up seeing is the sign of my coefficient flips, because now I'm holding constant this other factor that mattered. And before, when I was leaving this out, I was picking up not only the kind of effective police force expenditures, but also any variable I left off the right-hand side that was correlated with that. And so if I leave out unemployment, I was actually picking up the relationship of not only police force expenditures, but also the unemployment rate. When I include it in my regression, I'm no longer picking up the effect of the unemployment rate in my coefficient. And so I'm getting a more accurate kind of representation of the relationship between crime and police force expenditures. So the idea there is we are only picking up evidence of a correlation. You can imagine if one variable can impact this, well, there's probably a lot more than one variable that I'm leaving out of this regression that actually would help predict crime, right? So I want to be able to try to control for as many of the things that I think matter as possible. So we'll go back here and think about this idea of causation, right? Once I control for that unemployment rate, maybe I actually get that, this sign would flip, right? Or you can think about the other example, that birth weight and mother smoking. If I just run this simple, naive linear regression, well, there's a lot of other factors about the mother and the situation, of the pregnancy that would influence the birth weight, the age of the mother, right? Whether or not, the nutrition of the mother during the pregnancy, probably the average, the income level of the mother. And so if I don't include those things, this coefficient on whether or not the mother smokes will pick up some of the effects of all those other variables. So you can imagine here, I found a pretty large negative effect of smoking during pregnancy, but is that the actual causal effect? Because you had to guess, what's the relationship between maybe the income of the mother and smoking during pregnancy? It's inverse, right? You would think that as education levels or income goes up, it's less likely the mother smokes during the pregnancy. Well, we didn't include those variables there. So that smoking coefficient is going to pick up the effects of higher income, higher education levels. Well, people with higher income generally have better access to healthcare, right? They can afford vitamins, higher nutritional food. And so all those things we know probably have a positive effect on birth weight. In terms of birth weight being higher, generally means like a healthier baby. And so if we don't include those variables on the right-hand side, this isn't really a reliable estimate for the causal relationship. Yeah, those two things will be correlated, but it's because of all these other factors that we left out. So we want to try to include those factors. So another example I always kind of like to show, if I have autism rates in organic food sales, if I have that year by year in a data set, if I run a linear regression, it will be a strong positive coefficient, right? Autism rates and organic food sales are highly correlated. That doesn't mean that organic food sales are causing autism, right? There's a lot of other factors that are probably driving both these things. We've seen an increased attention to health, which means people probably are going to buy better food, but also more doctor's visits and probably identifying autism earlier in life and at higher rates. And so it's this outside factor, this general interest in health, that's actually driving both of these things that we're not entering into the equation, right? So what can go wrong, right? It's that we've got this outside variable Z that's causing both X and Y to change. So as we include more variables, well, it's less likely we've left out this important variable Z, right? That's driving both of these things. If once we get Z into our right-hand side there, added in as an additional control variable, we're now able to control for that factor, right? And it no longer is going to screw up that coefficient that we're looking at. So I always thought this was kind of funny. So I used to think correlation implied causation. Then I took a statistics class and now I don't. Sounds like the class helped. Well, maybe, right? Because maybe it wasn't the class that was causing me to understand this. It was the fact that there's other things, characteristics of myself that led to me taking the class that actually caused me to understand it, right? So let's go. I just don't have to worry about this. This is just I have a econometrics book I grabbed this from. Basically, all I'm getting at is here, if we leave out an important variable, this X2 variable, it wasn't included in my regression, then when I look at my slope coefficient, it's going to capture the true relationship between X and Y, but also this additional component. So we call this a bias, right? If we don't include these other variables like X2 that are influencing Y, our estimates will be biased, right? Now, once I include X2 in this regression, this bias goes away. And I actually capture what the actual relationship is between that X and Y variable. So this is why it's important to kind of include those variables we think matter on the right-hand side there. So I've got an example in Excel that we'll kind of walk through. So let me see. This should be under the in-class data folder on Canvas. And it's called GPA omitted variable. So I've got this data set of college students, and I have their college GPA. I had what their SAT score was, a 1-0 for whether or not they were a student athlete in college. This was some verbal math test they had to take, their high school rank, whether or not they were female, some race identifiers, the total credit hours they took, and this was over the course of their college career. Their high school size, which I forget, they moved the decimal on this, so it's probably would be my guess like 1.19 might represent 1,190, right? So it's just they scaled the variable. And then don't worry, I don't think we're going to use this SAT squared variable. So I'm actually just going to delete this for the sake of what we're doing, okay? At least for today. I might introduce that next week. So maybe I have this question of, is being a student athlete a positive or a negative when it comes to the GPA of a college student? And you can imagine it could go both ways, right? So maybe, being a college athlete, I learned how to work on a team. I have to have better time management skills. Maybe I learned, I'm learning all these life skills that help me be a better student. But at the same time, it's a huge time commitment, and it leaves fewer hours for me to spend on my academics. So it could go either way. I don't really know what this relationship is. So I'm going to go up here. And we said last class, just a reminder, I think on a Mac, instead of going to File, you'll go up to the Tools. So File, Options, or on a Mac, once you go to that Tools tab or Tools in the toolbar at the top, you should see this add-ins option. We'll manage our add-ins and make sure that Analysis Tool Pack is selected. And then under our Data tab, we should now have this Data Analysis. Okay. You guys working along, we were able to get that added in. How does it do on Mac exactly? It's Tools. Yeah. And then there is like a add-ins like halfway down, right? Yep, that's what I thought. Okay. Yeah, so it's once you get the tools, it's kind of you should be able to see the add-ins. So we're going to go to Data Analysis. We're going to go to Regression. We're going to hit OK. My Y variable, I want to try to predict college GPAs based off whether or not the person is a student athlete. So I select that college GPA variable. Then go to my X variable here. Scroll up so we can see what I'm doing. And I'm just going to select this student athlete variable, right? So I'm going to run this very simple kind of, I guess, somewhat naive linear regression where the only variable I've included on that right-hand side is whether or not they're a student athlete, okay? So I hit OK, and I get this output. We're going to look at a few things here. So the first is, I've got a bunch of things up here, and there's a couple different R's. We're looking at this as our R squared. These other measures are helpful, but outside the scope of this class. So here's our R squared. Now I said R squared is the percent of the variation I explained. In Excel, it gives it to you as a proportion. So, 0.008 here would be 0.8% of the variation. So we're not explaining a lot of the variation in GPA with just that student athlete variable. However, we can still look at the coefficient and see, oh, it's negative, right? So the interpretation is a 1 unit change in our X variable, which here, our X variable is just a 0.1. So going from being not a student athlete to being a student athlete, the predicted GPA would go down by 0.28, which, on a 4-point scale, that's a pretty sizable effect, right? The p-value, e to the negative 0, remember, move the decimal 9 places to the left, this p-value is 0. So this is highly significant. I can say at the 99% confidence level that I can reject the null hypothesis, which remember, my null hypothesis is always that this coefficient is equal to 0. Oh. Okay. So my null hypothesis is always that this coefficient is equal to 0. I'm rejecting that. I have a p-value of basically 0. So I can say that I can reject that there is no relationship, or I'm saying there's evidence that there is a strong relationship here between being a student athlete and college GPA. However, this is a pretty naive regression, right? I mean, if this data set, just to give an example, if it had D1, mainly D1 schools, what do you think is probably true about the admission standards of Alabama football players relative to the average student in Alabama? Probably a little bit lower, right? They're probably not quite as stringent. And so if I just run this naive regression, well, my student athletes, if they're more, lax on the academic standards, well, then of course I'm going to see that being a student athlete predicts that GPAs will be lower at the college level. So I want to try to control for like maybe the academic ability or the, I guess, for lack of a better intelligence level of the students. Well, if I go back to my data, right, scroll up here, I've got something that somewhat tries to control. Now, it's not a perfect measure. SAT definitely has some biases built in, and it's not the perfect measure, but it's some control that we could use for the kind of incoming college students' academic ability. So we're going to go back to our data analysis. We've got this regression selected. Excuse me. I've already got my Y variable selected as college GPA, so I don't have to change that. But now for my X variable, I'm going to include not only my student athlete variable, but this SAT score variable as well, right? So I'm just going to highlight both of these columns, Control Shift, hit the down arrow. So now it's going to run this regression, but it's going to include both student athlete and SAT as independent right-hand side or X variables, right? So I'm now able to control for the SAT score of the student athlete. Or these, sorry, not student athlete, but these students. So I've got my labels selected, I hit OK. I get the regression output from Excel, and it finds that, well, man, including the SAT score, I'm now not explaining 0.8%, I'm explaining what, 16.7% of the variation. So I'm able to make a lot better predictions than I was before, just by including this additional one variable. So I come down here, I can look at my slope coefficients now on both of these variables. So the interpretation of this SAT score coefficient, remember, it's a 1 unit change in the X variable. So if SAT is my X variable, if a student scores 1 point higher on the SAT, their predicted GPA would go up by 0.0019. Now that seems really small, but I mean, we're talking about the effect of 1 additional point on the SAT, right? So maybe I want to know the effect of 100 points higher on the SAT. Well, if this coefficient is the effect of 1 point higher, how could I get the effect of 100 points higher on the SAT? Simply, if scoring 1 point higher increases my GPA by 0.0019, scoring 100 points higher would increase it by 0.0019 times 100, right? If I know the effect of 1 unit, to get the effect of any other unit, I just multiply that by however many units I'm interested in, right? So the effect of 1 unit is 0.0019. The effect of 100 units would be that times 100. And that makes a little more sense, right? If someone scores 100 points higher in the SAT, you'd predict their GPA would be about 0.2 higher. That seems a little bit more reasonable, right? At least it makes a little more sense to talk about it in that context. And I didn't throw in there, that's the effect of 1 additional point on the SAT score, holding constant whether or not the student was a student athlete. So 2 students who are both student athletes, one of them scores 1 point higher, the additional expected increase in their GPA would be 0.0019. We can also interpret this athlete variable. So it's still a 1 unit increase in the X variable, which if it's a 1, 0 variable, it's just going from the group that's a 0 to the group that's a 1. So going from not being a student athlete to being a student athlete would change the predicted GPA by, the GPA would go down by 0.05, holding constant what the SAT of the score of the individual was. So the thought experiment is like, if I have 2 people with the exact same SAT score, but one of them is a student athlete, their predicted GPA will go down by 0.05, okay? And that's a lot more powerful because we're holding constant this measure of kind of their academic ability. Now, the p-value associated with that student athlete variable now is 0.26. So here, am I going to be able to reject at any of my conventional levels? Well, we only reject if the p-value is less than alpha. 0.26 is not even going to be less than my alpha of 0.1. So I fail to reject the null. Well, if I fail to reject the null with these linear regression examples, I'm really saying I can't reject that there's no relationship. Right? So I can't really say that there's any relationship between GPA and being a student athlete because I failed to reject that null, but that coefficient was equal to 0. You can imagine, if I have, if this coefficient is 0, well, then it doesn't matter. If this x variable changes, anything times 0 would be, not influencing that y variable. So we went from thinking, man, we should encourage, here was our, I guess we could rename this. Oh, no, here was my data. Here was the first regression we ran. So this was my naive regression. If I ran a very naive regression, I'm like, oh man, I should never encourage someone to be a student athlete, right? It really hurts your GPA. I then say, well, if I just control for their academic ability, okay, well, doesn't, maybe there's some evidence that it has a negative effect on your GPA, but I can't say with any decent level of confidence that it really has an effect. Well, then I could go a step further, right? I don't just have SAT scores. I've got a bunch of different other variables that I think could help me make better predictions about someone's college GPA. Excuse me. So I go back to my data analysis tab, regression, hit OK. I've still got that y variable selected, so that's nice. But now for my x variables, I'm going to include every single variable I have in this data set, right? All these things seem like things that I might want to control for. So I just Command Shift on a Mac, hit the down arrow. I've got all of those variables now. I'm going to be including all of them on my right-hand side. So if our R squared before was 16.7, I would imagine it goes up quite a bit by including all these additional control variables, right? So we'll see if that's the case. Oops. Sure enough, I went from 16.7 to 29.3%, right? Or the proportion of the variation I'm explaining is 0.293. So, I mean, it's not, we would like this to be a little bit closer to 1, right? Representing 100% of the variation we could explain, but, it did almost, double by including these additional control variables. So we now scroll down and we can kind of see, here's all of my variables on the right-hand side and their associated coefficients and their associated p-values. So if I'm looking at this and I now want to interpret the coefficient on being a student athlete, well, now it looks like going from not being a student athlete to being a student athlete, it would actually predict that GPAs go up by 0.17. And the p-value is basically 0. So I can say that with a high level of confidence, 99% confidence, that I reject the null hypothesis, that there is no relationship, or that I found strong evidence that there is a relationship between being a student athlete and college GPAs. And in fact, it's a positive. And that's because I'm able to control for a lot of other factors. So the thought experiment now, remember, that's the interpretation, holding everything else in the regression constant. So two people with the same exact SAT score, same score on this verbal math test, same high school rank. They're both either female or not. They both are of the same race. They both have the exact same total number of credit hours. They both went to a high school of the exact same size, but one of them was a student athlete and one of them wasn't. We would expect their GPA to be 0.17 higher. That's a lot more powerful, this statement, right? Holding constant all those other factors, now the effect of being a student athlete looks like it's actually positive. Any questions on that idea? So, this kind of shows that when we're omitting variables that are important, we can draw very incorrect conclusions. So I'll call this one, we threw the kitchen sink at it, right? We threw every variable that we have at this regression. So when we started out very naive, we would have come to the exact opposite conclusion, right? And that's because this student athlete variable was picking up all the effect of all these other variables that we left out. But then once we included them, well, now we were getting a much more probably accurate representation of what the true relationship is between college GPAs and being a student athlete. Any questions on that? So there's a couple more things I want. So one thing you could do, maybe like a question you could expect in the exam or something. is I look at this output and I want to know which of these variables could I say have a significant relationship with my Y variable of college GPAs. Well, remember, if we can reject the null, we can reject there's no relationship, or we're saying we found that there is a significant relationship. So basically, to find out which variables have a significant relationship with college GPAs, we want to be able to say, well, for which of these variables can we reject the null hypothesis? So all I'm going to do is compare, is this p-value less than alpha? So maybe I say, is this significant at the 99% level, right? Which of these variables? Okay. And one thing that we won't really use are these upper and lowers. So I'm just going to get rid of these here real quick so I can kind of show you the variables and then what we're doing. So I've got these p-values. What did we do with hypothesis testing? Like the two population examples, we use this if statement. Right? So now we're going to say, okay, if the p-value on this variable, I start out and do the intercept, but I can do this for every variable, is less than, well, we'd had 99% level, so our alpha is 0.01. Right? If that p-value is less than 0.01, put in the word reject. If it's not, put in the word fail to reject. Right? And then when I copy this down, it's going to compare every single p-value to that alpha of 0.01, and I'll quickly be able to determine which of these variables can I reject that null hypothesis at, right? And if I'm rejecting the null, what I'm really saying is I found that there's a significant relationship between this variable and my dependent variable, or the Y variable, in this case, college GPAs. So I copy this down. Very quickly, I can see almost every variable in this regression has a significant relationship with GPAs, with exception to this verbal math score and kind of the race identifier, right? So looks like kind of race isn't necessarily great, kind of, doesn't give me any additional predictive power in predicting GPAs. And also this verbal math score doesn't look like it's very good at predicting what someone's GPA will be. So, if I'm a university and I look at this, I'm like, well, man, I can't say that this verbal math score has any effect on GPA, predicting GPAs other than 0. Maybe it's not a very reliable, measure of the student's actual ability. And so maybe I scrap that, right? But one thing, I don't know, there's a lot of discussion. I know that like Ball State doesn't make you submit SAT or ACT scores now. And I'm not saying that they necessarily should, but, just from this one sample, it looks like, well, man, if I'm an admissions department and you tell me I can't get a student's SAT score, I mean, it is highly significantly correlated with college GPAs, right? I'd probably be not very happy if I'm an admissions, person. I look at this, I'm like, well, man, I can't use one of the things that is actually a really good predictor. But this kind of shows like we could start to make the, use this linear regression to make those decisions or statements like that, right? That, hey, if I'm working in the admissions department, I'd love to have the student's SAT score. This verbal math score or test that we're giving them, let's scrap that, right? That's not very accurate at predicting their GPA at all. Any questions on that? And we don't have to do it just at the 99% level. We can compare to any alpha here. So I could, for instance, let me see if there's an interesting one. So I'm making these statements about the verbal math score, and it's not significant at the 90% level. But if I'm looking at this p-value, it's really close, right? I mean, it's just barely greater than 0.1. And so at the 90% level, I could almost reject that null here, right? But so it's probably don't want to like completely scrap it. Like, yeah, it's not significant at the 90% level, but it's significant at the 89% level, which, we're kind of splitting hairs here. What level do we draw the line at? 90, 89%, is there really a difference there? So these are things we can start to think about, right? Making our rejection decisions. One more thing I wanted to show you, and I'll go back to here. Did I have yeah, so here I've got the same output, but kind of completed. So I want to show you a way that we can make predictions. Okay? So here's my kitchen sink one, and I deleted some of the stuff so we can see what's going on. So let's say I have this hypothetical student, and I want to try to predict their GPA. So I'm going to think about what their values are going to be for all these different X variables. So for the intercept, well, that's always going to get added into my regression. So I'll just put a 1 there, right? We'll kind of see why this helps me in just a second. Let's say this person got a 1200 on their SAT. They were a student athlete. Their verbal math score, I believe this is ranges from 0 to 1. So let me double check on this. Yeah, ranges from 0 to 1. So let's say, I don't know, they got like a 84 on this verbal math score. Their high school rank, let's say that they were 15th ranked in their high school. Let's say they're not female, they're male. And so this identifier for being female, if the person isn't female, this is just a 0. And then, you know, I don't know, I could say maybe they're a race other than white or black, right? You know, a race other than those two. Their total credit hours, let's say they've taken 55 credit hours up to this point, and their high school size, this was the one where, you know, it was in the thousands, so they moved the decimal. So let's just say it was like 2,300 or 2.3, right? As how. So we just took basically this hypothetical person and all the values that they had for these X variables. Well, now what I'm doing in my regression is, if I'm trying to predict GPAs, well, I now have values for everything. So like, you know, maybe my intercept was 10 and the coefficient on SAT was 2.1 and the coefficient on athlete was 0.23. I'm going to have this long equation, but I now have this person, all the values for these X variables. So if I plug this hypothetical person's values in, I now just have a long equation that's just like this plus this times this plus this times this, right? I just have a pretty simple long equation. So I'm just going to go through and for each variable, take the coefficient, multiply it by whatever the X value is for this hypothetical person, and then add them all up. Well, a really easy way to do that in Excel, I've got their X values here. I've got the coefficients. I could just go take the coefficient, multiply it by the X value. So now you can kind of see why putting that 1 there for the intercept, well, that way the intercept always gets added in, because it should be, right? When I'm looking at that regression equation, the intercept will always get added into my prediction, regardless of what the X values for that individual are. And so once I have this set up, I can copy this down. Notice when the person isn't in that category, well, I shouldn't be adding anything into my prediction then, right? Because this was the effect of being female. Well, this person wasn't female, so that shouldn't get added into my prediction. Now I've got every single X variable times its coefficient. Now it's just a matter of adding those all up to get my predicted GPA. So this person, we would predict their college GPA would be 3.16. And we could look at what their actual, you know, this is like a hypothetical person. So it's almost like we're making projections. So you can imagine like an admissions department or something, like they would love to do something like this, right? Because they want to try to predict like how successful is this student going to be once they get to our university. Any questions over anything? I went a little bit quick there kind of at the end. That file I had up there had a similar example. I think the X value, the hypothetical person might look a little bit different, but it's the same kind of general idea. I just wanted to make sure that we kind of walk through and explain kind of why that was in there, how we would have created that. Any questions on any of that? So hopefully you can kind of see the power of linear regression starting to come out. This omitted variable idea that, you know, we want to make sure if we've got additional variables we think matter, we want to include them on the right-hand side there. So on Monday, we're basically going to just be going through more examples, right? So I've got a few kind of in mind, some data sets that I think might be interesting. So we'll kind of work through some of those. And then next week, you know, I'll just seeing more of this, just I think will help and kind of make it easier as we work through this. But yeah, any questions before I let you guys out here? All right. So this should be very helpful in completing the rest of the Excel and the Connect Home, that 5th Excel and Connect homework. If you are going to, you know, planning to do those, things that we talked about today kind of should cover the gamut of things that it will be asking those assignments. Right? So have a fun, safe weekend. Enjoy what's supposed to be beautiful weather, and I will see you guys on Monday.